So earlier in this unit, we talked about that if you add a solute to a solvent, that it will, whenever you do that, it changes some of the properties of the solvent. We talked about, remember, with you adding something into water, is that when you did that, is that it changes, say, the surface tension of the water, changes how well the water, wets to surfaces. It changes the boiling point and the freezing point and what the vapor pressure is, and we talked about all those things. And so, decreasing the vapor pressure, the freezing point, and increasing the boiling point. And so we're going to look at two of these properties right here in this lesson. We're going to look at basically at changes the freezing point and changes the boiling point right here. Now, for these two things, the freezing point, the decrease in the freezing point, and an increase in the boiling point done by adding a solute to a solvent, is it turns out the degree to which these properties change depend only on the number of solute particles, not on the particle size or their mass or on what substance they are. And so if I have, n number of particles of solute in a particular volume of solution, that will have a certain boiling point. Whereas if I have a different type of substance, but I have the same n number of particles, it will have the same boiling point as the other one. Even though they're completely different substances, even though the solutes have completely different masses, even though those atoms or those molecules inside may have completely different sizes, it doesn't really matter what they are or how big they are. All it matters is what number of them there are. And so these types of properties, such properties that depend only on the number of particles but not on anything else, are called colligative properties. And turns out that our freezing point change whenever we have a solution and our boiling point change when we have a solution are both colligative properties. They depend only on the number of particles of the solute, not on anything else about the solute. Now, we will find there are some other issues that are involved here, molality and what the solvent is. But in terms of the solute, all that matters is how many particles that you have. And so let's go ahead and take a look at the first of those right there, which is going to be on freezing point depression. So, we've said before, the addition of a solute will lower the freezing point of a solvent. And it will lower it according to this equation that you see on the screen. Delta TF is equal to M times KF times I. Looks like a fairly, not a long equation, but somewhat complex here. So let's look at the pieces here. First one we're going to take a look at is delta TF. And so delta TF is the freezing point depression. That is, it is the amount by which the freezing point of a substance drops whenever you add a solute to that substance. And so it's the amount the freezing point decreases. The units we're going to use is going to be degrees Celsius. Kelvin would work here, but usually when we talk about freezing points, we're typically dealing with things that are in degrees Celsius, so we'll use that here. M, right here, it's a lowercase m. And if you remember from what we did before, is lowercase m is molality. And so m is the molality of the solution, and it will be measured in molals, as we've discussed before. KF. KF is a constant. It is we'll usually call it the freezing point depression constant. Sometimes you will hear a little more of this sort of technical sounding term, cryoscopic constant. Those are both exactly the same thing. And it's the freezing point depression constant of the solvent. And so the key thing about KF is remembering that it is about the solvent. It has nothing to do with the solute, nothing to do with the solution overall. It's of the solvent. So different solvents have different values of KF. For water, KF is 1.86 degrees Celsius per molal. And so no matter what we mix into water, doesn't matter what the solute is that KF for water is always going to be 1.86. If we are mixing into a different solvent, into alcohol or something else, then it would have a different value of KF than 1.86. But for water, it's 1.86 degrees Celsius per molal. Our last one here is I. I is called the Van Hoff factor. Dutch guy, that's why he has this sort of weird name. But basically, the Van Hoff factor deals with this issue of the fact that we said this was a colligative property. And colligative properties are based on the number of pieces, not on what they are. And the Van Hoff factor, I, is the number of pieces into which the solute molecules will break. Now, we need to go into that in a little more detail, and that's what we're going to do in this next slide here before we get back to working out some examples on our freezing point depression. And so let's take a look at the Van Hoff factor. So finding the Van Hoff factor I. if you have an ionic solute, so we're going to talk about ionic solutes to start with. Ionic solute molecules break apart into their constituent ions when dissolved, creating electrolytes. And so if I were to have something nice and ionic like NaCl, and so NaCl is ionic, and because of that, whenever it's going to break up into our sodiums. Remember, the sodium is going to lose an electron, so it'll be positive, plus the chlorines, which are going to gain an electron, are going to be negative. So it breaks up into two ions. In this case, so for NaCl, the Van 't Hoff factor is going to be simply equal to 2. Okay? So ionic solute molecules break apart into their constituent ions when dissolved, and then you have an electrolyte. The Van 't Hoff factor is then the total number of ions in a molecule. So if we had BaCl2, this is going to break into 1 barium ion and 2 chlorine ions. And so for a total of, that shouldn't be 2 right there. That should be 3. So let's get rid of that one right there. That should be a total of I equals 3 for this case, because of the fact we have 1 barium and 2 chlorines. And so Van 't Hoff factor for this first one is going to be 3, BaCl2. If we have H2SO4, is that this is going to break up into 3 ions. The reason why is there are going to be 2 hydrogens, but this SO4. If you look at that SO4 right there, is that SO4 is sulfate. That's a polyatomic ion, and there's only one of them here. And so we have 2 hydrogens and 1 sulfate ion for a total of 3. So it's one thing you need to watch out for is that whenever you're dealing with something that's an ionic substance, if it has a polyatomic ion, remember those polyatomic ions are going to break apart separately. They always travel together. And so H2SO4, 2 hydrogens, 1 sulfate for a total of 3 for your Van 't Hoff factor. Non-ionic solute molecules don't break apart at all. Remember, that's why they're not called non-electrolytes. Remember, as they don't break apart, they don't have ions, and so as a result, there are no positives and negatives to carry current through the solution. And if they don't break apart, then they'll simply have a Van 't Hoff factor of 1. So they break into one piece. They really don't break at all. So looking at things, first thing you want to do if you're trying to figure something out is you want to identify, is it ionic or not? And remember that typically ionic substances tend to be made of things that are basically one of the alkali or alkaline earth metals with something that's on the far right side of the periodic table. Well, not the far right, so it doesn't count the noble gases, but something like a halogen or in the same column as oxygen or something like that. Or it's a substance that has a polyatomic ion in it. If either one of those two things is true, you know it's going to be ionic, and you're going to have to count the ions it breaks into. Things that are non-ionic tend to be things that come from sort of that section that's around column 4 in the periodic table, the one that should be 4A, the one that sort of has carbon around in it. So like carbon dioxide, CO2, is not ionic, and so it'll have a value of 1. I just gave away one of my examples down at the bottom. So that's something that you do want to look out for there, is that if it ever says it doesn't conduct electricity in the solution, you know it's a non-electrolyte. And if it's a non-electrolyte, that means it doesn't break into parts. And so as a result, it has a Van 't Hoff factor of 1. So let's try to do some examples here. What is I for the following? So Na2O is our first guy right here. And so for this, first question is this ionic? You look at sodium. Sodium's way over there on the left side of the periodic table. It is over in our alkali metals over there. And so that with an oxygen, which is over on the right side, this is definitely going to be ionic. We have 2 sodiums and 1 oxygen. So your I value here is going to be 3. Okay. Carbon dioxide. We already sort of talked about this one, but carbon and oxygen are both sort of next to each other in the middle here. Neither one of them particularly wants to give up an electron, and so as a result, this is going to be a covalently bonded thing. It's not ionic, and since it's not ionic, its I is going to be just 1. NH42S. In this case right here, NH4 is ammonium. That's a polyatomic ion. And we have 2 NH4s here, and we have 1 sulfur. And so I for this one is going to be basically 3. That is ionic. C6H14. This is a hydrocarbon. We have a carbon and a hydrogen here. Is that, in general, all your hydrocarbons, things that are just made of carbon and hydrogen, and maybe carbon, hydrogen, and oxygen, are not going to be ionic. They're all covalently bonded. So typically things that tend to start with carbon like this are, you could pretty much say 99.9% of the time, are going to be covalently bonded, not ionic, and so I is equal to 1 for that. MgCO3. Ionic or not? Hint is CO3 is carbonate, And so polyatomic ion, we have one of those carbonates and one magnesium for a total I value of 2, like that. HCl, also ionic. Chlorine is over there in the halogen column. Definitely wants to steal an electron, and hydrogen's more than willing to give it up. And so we have one hydrogen ion and one chlorine ion for a total I value of 2 as well. And so that's how you go about working out and figuring out what the Van 't Hoff factor is for different solute, different possible solutes here. Boiling point elevations, our next thing. Boiling point elevation works very similarly to freezing point depression. Just some different variables that are in there. If you look at the equation, it looks almost the same. The only difference really is we have some B's where last time we had F's. So the addition of a solute will raise the boiling point of a solvent according to the following equation. Delta TB equals M times KB times I. In this case right here, our delta TB right here, the delta TB is the boiling point elevation. It's the amount the boiling point increases by in degrees Celsius. And so when we talk about that delta TB, the delta, remember, means change. So change in the temperature of boiling. So that's what we have for that one. M, same as it was before. It's the molality. KB is the boiling point elevation constant. Sometimes it's called the Scopic constant. That's the more technical term. But boiling point elevation constant is what I'll usually use, or what we'll talk about in this class generally. So KB is the boiling point elevation constant, and it does, like KF, depend only on the solvent. And so for water, KB is 0.512 degrees Celsius per molal. Different substances, of course, would have different boiling point elevation constants. And so this is sort of what we've got for right here. I, once again, is our Van 't Hoff factor. It works the same way as it did for freezing point depression. And so breaks the number of pieces of the molecules, the solute molecules will break in 2.